in 1781. The other planets, of course, were known even to ancient astronomers. But apart from some moons and an occasional comet, this is pretty much what scientists knew about the contents of the solar system. Well, then along came this fellow, Giuseppe Piazzi, a mathematician and astronomer, and he got the new year off to a good start. He discovered a new planet. Modern astronomers had only ever discovered one planet, and so this was quite a significant event. And I'm going to show you a high-resolution photograph of what Mr. Piazzi discovered, and that's here. She's Ceres, the goddess of agriculture and grain. And she's often depicted with her harvest bounty here and her crown of grains, and depending on the particular artistic interpretation, a scythe or some other kind of farming implement. It depends on the particular choice of the artist. But if you had cereal this morning, then you owe a debt of at least etymological gratitude to Ceres. So this is what Mr. Piazzi discovered. And now this is the same chart I showed you a moment ago, the planets as they were known in 1800. And this is the planets as they were known in 1801. And so Ceres fit very nicely into this gap between Mars and Jupiter, and for much of the next half century was considered to be a planet like the others. And in fact, if you come to the dwarf planet discussion on Sunday, you'll hear more about this perception of planets in the first half of the 19th century. Well, then along came this fellow, Heinrich Wilhelm Olbers, who was trained as a physician, but was a fantastically productive astronomer. He made many, many important contributions to astronomy. And the very next year, he discovered another new body in that part of the solar system. But more importantly, what I want to tell you for the dawn story, in 1807, he discovered still another new member of the solar system family. And I'll show you a high-resolution photograph of what the good Dr. Olbers discovered. She's here, the Vesta, the Roman goddess of hearth, home, and family. It's interesting, Vesta was worshipped privately in the home, and so there are fewer surviving records of exactly how she figured into Roman mythology than there are for many of the other gods and goddesses. Of course, people are familiar with the Vestal Virgins, but I'm referring specifically to the goddess Vesta herself. She's rarely depicted in art. When she is, she often has this very stern look on her face, but I hope to convince you that the solar system body Vesta is a much happier place. So this is what Dr. Olbers discovered. And now, this is the same view I showed you earlier, but I've zoomed in so Jupiter is the outermost planet. And you can see Vesta also fit nicely into this gap between Mars and Jupiter. And it as well, until the middle of the 19th century, was widely considered to be a planet. Well, then technology and science advanced until more and more and more bodies started to be discovered in this part of the solar system. And now it looks something more like this. And after my presentation, those of you who are in the back, if you want, can ask the people who are sitting in the front to confirm for you that I've added 10,320 individual dots to this chart to show you that number of asteroids. Now, we know about many, many more asteroids than that. If I showed you all of the ones we knew about, this part of the chart would be nothing but an uninterpretable yellowish green. So I'm only showing you the ones that are larger than about 10 miles or so across. But what this shows us is this part of the solar system is very different from the rest of the solar system. You can see the inner solar system is nearly devoid of these bodies. And in fact, if we zoom out, you can see especially clearly that there's something special about this part of the solar system, which of course we call the asteroid belt, that distinguishes it from both the inner solar system and the outer solar system. And so the question is, why is that? Why is this part of the solar system different? Well, you're a great audience for asking that question. I appreciate it. The next part of my presentation is to give you a sense of the reason. But to do that, I have to take you back in time a little bit before Piazzi's 1801 discovery of Ceres. In fact, I have to take you back to the dawn of the solar system. Get it? I'm telling you about the dawn mission. Okay. You get it. So, this is a photograph from the Hubble Space Telescope of something which, in fact, if you're an amateur astronomer, you may have seen yourself. This is part of the Trifid Nebula in Sagittarius, although if you saw it, you probably didn't have quite as good a view as Hubble did. And what we see here is a large interstellar cloud of gas and dust. And off the top of the view, up here, outside of Hubble's picture, is a brilliant star. And the light of the star is so intense that as it shines down on this cloud, it's blowing this material away. It's almost as if it's evaporating it in interstellar space. And yet up here, there's a knot of material so dense that it's blocking the light of the star and preventing it from sculpting the dust here. So this material is, in essence, in the shadow of this dense knot. And that's why it's sticking out of this cloud like a finger. And deep inside here are conditions that we believe are very much like those that gave rise to our solar system 4.6 billion years ago. Because the material is so dense that eventually it's going to collapse under its own weight and form a star. And that's how our star, the sun, formed. And once we've formed a star, then we can begin to form planets. Because now we have this big swirling cloud of debris, particles flying around, and sometimes these particles will hit. Now sometimes when they hit, they'll break apart. Other times, however, they'll stick together. And so two particles will hit and stick together, and we can see that happening right here. And then another particle hits and sticks to that, and another particle, and another particle, and another particle. And so gradually, these grow larger and larger. Now, on the chart, they're growing larger to form words, but in space, they grow larger to form rocks. And gradually, these rocks become still larger to form planets. We believe that's how the rocky planets of the inner solar system, one of which is right under our feet, formed 4.5 billion years ago. However, when massive Jupiter formed, its gravity was so intense that it interrupted this process and deprived the material nearby of the opportunity to continue growing to become full-size planets. And so Vesta and Ceres are often described as protoplanetary remnants, or simply protoplanets, because they were in the process of growing to become full-size planets when their growth was cut off by Jupiter. And Dawn's mission is to fly out to the asteroid belt and study these bodies. So, let's summarize the motivation for the mission. We want to compare Ceres and Vesta in order to get insights into the conditions and the processes that were acting at the dawn of the solar system. And these are the two most massive asteroids, the two largest bodies in the asteroid belt. And although they're very similar distances, you saw that from my earlier chart, they're very different bodies. Ceres apparently has remained cool throughout its entire history and perhaps even retained water. And I'll tell you more about that in a moment. Whereas Vesta was known from telescopic evidence, apparently became very hot sometime in its past and seemed to be largely devoid of water. And so it's almost as if these two bodies straddle what some astronomers would call a snow line or a dew line or a frost line in the solar system. Vesta, just a little bit closer to the sun, is like the rocky bodies of the inner solar system, Mercury, Venus, Earth, Moon, and Mars. Whereas Ceres is more like the icy moons of the outer solar system, the icy moons of Jupiter and Saturn. Now, I think when most people think of asteroids, they think of sort of chips of rock, right? They're maybe the size of buildings or mountains. And that's how I think most people think of asteroids. But these are very different bodies. Vesta, the smaller of the two, has an equatorial diameter of 350 miles. And Ceres is 600 miles in diameter. So these are big places, and we can put them into context by comparing them with other bodies. Now, Matilda is the largest asteroid a United States spacecraft had visited prior to the Dawn mission. And Lutetia is the largest asteroid any spacecraft had visited. The European Space Agency spacecraft Rosetta flew by Lutetia in 2010. And also, in the interest of full disclosure, I should tell you that I've exaggerated the size of Matilda here so it would occupy a full pixel so that you could see it. What this shows us is Vesta and Ceres really are of an entirely different scale. They're nothing like typical asteroids. In fact, they're more of the scale of other sorts of solar system bodies that you may be familiar with. And undoubtedly, everybody remembers in 2006 when the International Astronomical Union created a new category of bodies, dwarf planets. Pluto was put in this category, and oh my God, everybody thought this was awful. How could we be so inconsiderate? And why didn't Earth take into account Pluto's feelings in this matter? And why didn't we think more about how it might feel about this decision? Well, whatever you think of that decision, at the time the category of dwarf planets was defined, Ceres was put in that category as well. It satisfies all of the attributes of a dwarf planet. And in fact, it was the first dwarf planet discovered 130 years before Pluto. And Dawn will be the first spacecraft to visit a dwarf planet. Now, to me, what this says is, these are not just little chips of rock. These are big places. In fact, to me, really, Vesta and Ceres are among the last unexplored worlds in the inner solar system. And that's what I think is one of the things that's so cool about a mission like this. We're not just going out and looking at chunks of rock. We're truly exploring uncharted worlds. And I think that is really neat. But when you look at a picture like this, it's deceptive. Because California is mostly flat, right? But these are round, three-dimensional places. So they have much more area than is depicted in a flat chart like this. And so if we go into the third dimension, we can compare the surface of Ceres with that of the continental United States. So this is a Hubble Space Telescope map of Ceres, and as is often the case in these astronomical photographs, the color here doesn't tell you anything about the color of Ceres. Of course, it's encoding some other scientific information which isn't pertinent for our discussion. And Hubble couldn't see all the way to the North Pole or all the way to the South Pole, but the white rectangle I've drawn around it shows the entire surface area of Ceres to the same scale as that of the United States. And sure, Ceres isn't as big as the United States. Ceres isn't as big as Earth, but it's still a big place. It's 38% of the area of the continental United States. And if you just think about how vast and varied and frankly beautiful the geography and topography and geology of our country are, it suggests there's an opportunity for a lot of diversity on a place like Ceres, a lot of different things to see. And again, that's part of what makes it so exciting to go think about exploring it. So let's take a little bit more careful look at Ceres. Here it is in a set of Hubble Space Telescope photographs. And unfortunately, powerful as Hubble is and large as Ceres is, it's still far away, and it's not all that large, and so you can't really see much in these images. It's round and perhaps looks sort of planet-like as it's rotating, and if you have a good imagination and a pure heart, you may even see some features moving across the surface, but you can't really make out a whole lot in it. And so instead we have to resort to an artist's concept. And if my silly computer would be cooperating here, no, it's not what I wanted you to see. Rather, I wanted you to see that it's believed to be covered with a thin, sort of dusty crust. And deep inside is believed to have a rocky core. But between that core and crust, it's now believed that there's a thick layer of water ice, and perhaps even liquid water. So Ceres may have subsurface ponds or lakes, or even oceans of liquid water. I think this is really quite remarkable, and it was just announced a few months ago in January that now water vapor has been detected around Ceres. And this is a very firm detection. It was observed with the European Space Agency Herschel Space Observatory. And so now the belief is that there may either be ice on the surface of Ceres, which is sublimating directly into space, or there could be cryovolcanism. So think of the word cryo, cold, volcanism. So that is water being forced up into space, erupting just as lava does from volcanoes on Earth and Io. And so the opportunity now to send a spacecraft there, and we have one already on its way, to determine what's going on, what's the source of water that's being liberated into space, and what's the nature of the water on or beneath the surface. I think that presents a really exciting opportunity. And so what Ceres really will look like, of course we don't know. Perhaps in Spacefest next year I'll be able to tell you, but this is what at least one artist perceives it to look like, with perhaps a lot of cracks and other features on it indicative of a largely icy surface. And there may even have been some interaction between the subsurface liquid water and directly on the surface. And so there may be evidence on the surface of alteration by water. So that's Ceres. Now let's take a look at Vesta. And here it is in the best view we had prior to the Dawn mission from the Hubble Space Telescope. And if we follow the shape around, starting from here, if you go around this way, it looks pretty much planet-like. It's even a little bit flattened at the North Pole, like your planet is. But when you come around here, you would expect the bottom to be a little bit smoother, to look something more like this. But plainly, that's not the way it looks. And so when astronomers got these pictures at the end of the 1990s from the Hubble Space Telescope, they concluded that what we were seeing is a large impact crater here with a big mountain in the center. And you often see mountains in the center of big craters. You've seen that in pictures of big craters on the Moon or Mars. And of course, the reason for that is the way you make the craters, you take a big piece of interplanetary debris, and it comes screaming down into the surface, and it hits the surface with so much energy that the rock essentially melts, and it flows away from the impact, and then it sloshes back. And as the rock sloshes back, it solidifies. And so that mountain in the center of these big craters is like a snapshot of the process by which that crater was formed. And so I want to show you an artist's concept of how this crater was formed by this big piece of interplanetary debris. So here's the big piece of interplanetary debris. Here's Vesta before the impact, and now here's Vesta after the impact. And this impact excavated a tremendous volume of material and sent all these rocks out into space, many of them to go on their own independent orbits around the sun. And some of those rocks may have made their way to the part of the solar system where you spend most of your time. And if they did, they could even have been pulled into our atmosphere. And perhaps if you've been lucky enough to see a meteor some night, you've actually seen a piece of Vesta burning up in our atmosphere. Now, when I say that, I'm not just being poetical or clever, although I am poetical and clever. I'm being serious, because this actually is a photograph of a meteorite from Vesta. These are very common. I took this picture myself in a museum. Because it's now known that 6%, and think of this, 1 out of every 16 meteorites seen to fall from Earth came from that one impact at Vesta more than 1 billion years ago. Now, maybe you know we have, I'm sure everybody's heard we have meteorites from Mars. Maybe you know we have meteorites we believe to be from the Moon. But we have far, far more meteorites from Vesta than we do from the Moon or Mars. And those are the only 3 solar system bodies to which we have linked specific meteorites. These are very, very common. You can find these everywhere. In fact, I can even find one right here on this desk. You can come up and take a look at this if you want to afterwards. And I bought this myself long before I became involved in the Dawn mission, just because I thought it'd be neat to have a meteorite from Vesta. And so the opportunity to have studied these for decades in the laboratory and now have a spacecraft at that location and study this material in its geological context really presents another, I think, very exciting scientific opportunity for this mission. So those are the meteorites, but let's get back to Vesta itself. So here again is Vesta before Dawn arrived, and now this is what Dawn showed us. And of course, we got in closer and saw something more like this, and revealed truly a whole new alien world. And some of the things we can see here, this was one of the first features that just became easily recognizable, and we nicknamed it the Snowman. And for scale, this crater is about 45 or so miles across. This, and I'll show you more about this later, this is the big impact crater at the South Pole with its mountain here. And up here, I don't know how well you can see it here, but again, we'll see this in some later views, is a vast network of chasms around the equator, many of them larger than the Grand Canyon, extending for literally hundreds of miles, that are believed to be a scar from the impact here. It sent so much energy reverberating through Vesta that it almost completely destroyed Vesta. Fortunately, it didn't, or we wouldn't have had a place to send the spacecraft. But it had so much energy that it disrupted the surface here hundreds of miles away and left this vast network of canyons. Now, we took 31,000 pictures while we were orbiting Vesta. Unfortunately, I don't have enough time allocated today to show all of them to you. So I put them together into an animation to show you what it would look like if you were there. And as we start here in the northern hemisphere, one of the first things you'll notice is the northern hemisphere is much more densely cratered than the southern hemisphere. Why is that? Because this big impact at the South Pole essentially resurfaced the entire southern hemisphere. And so the record of cratering from debris raining in from the asteroid belt had to start over about 1 billion years ago, whereas the north has had 4.5 billion years of cratering. And as we're moving farther into the southern hemisphere here, now you can begin to see this is part of the wall of that south polar crater. That crater is 300 miles in diameter. Think of this is extraordinary. There's nothing like that here on Earth. And unfortunately, I'm at such an angle, I'm having a little bit of trouble seeing the mountain in the center, but I think this is it here. This mountain, and again, I'll show you more views of this as well. This mountain is 110 miles across at the base. This is huge. And here again is part of the South Polar crater. To scale, that is compared to the size of Vesta, if there were a crater of this size on Earth, it would extend from Washington, D.C. to Tokyo. This is truly an extraordinary crater. This is another picture of this triplet of craters, the snowman. And to be perfectly honest, the reason I included this picture is because I think it's really neat. You can see a great deal of detail in this crater here, including fairly significant variation. There's a lot of bright material here and dark material in other locations, and it's believed that the bright material is subsurface, is rock, original rock from Vesta that had been buried and then was exposed when this crater was created. And the dark material is material that was brought in from elsewhere in the asteroid belt by impactors. And at the bottom of the crater, there are many small pits that look just like phenomena observed on the surface of Mars in craters. And these are interpreted to be from the escape of volatiles, in particular water, that was buried under the surface, perhaps brought in by other material from elsewhere in the asteroid belt. And then when the impact occurred, this material evaporated and left these pits as it departed. And you can also see here some of these chasms going around the equator, near the equator, and you can also see the densely cratered northern hemisphere here and the much more lightly cratered southern hemisphere here. Now, I included this picture because we saw a lot of these, and when we first saw them, we frankly didn't know what it was we were seeing. So this looks like a pretty conventional crater, night-sharp rim, but there's something different here. It's very subdued for some reason. Well, when we flew down a little bit closer, we got a picture more like this, and it's still not entirely clear what you're seeing, although you can see certainly more detail on this crater, some striations along here. But we not only took conventional pictures like this, but we also took pictures in stereo so that we could build up a good topographic map. And now what we begin to see is that this crater formed on a steep slope. And so this is the uphill part of the crater, and this is downhill. And so apparently what has happened here, and many other craters like this, is Vesta has a very rough topography, much more topographical variation than Earth does. Once the crater formed, the uphill material slumped because of Vesta's gravity, and there was this big landslide. Now, this crater is about 11 miles or so in diameter, so now there's this landslide 11 miles wide that comes screaming down this crater, and it built up so much momentum that it passed right through the bottom of the crater. Its momentum carried it up over the downhill edge and deposited all this debris over the downhill edge of the crater, and that's what left this very soft, subdued view here. And we can fly around and take a more careful look at it. So here's the downhill side of the crater. This is the uphill, and I'll freeze it. Again, I have a little bit of trouble from this perspective seeing it, but it looks like maybe right about here we're looking downhill, and you can even see some of the striations here left over from this landslide as it went down and passed right through the bottom of the crater and then left this large debris field on the downhill side of the crater. And in fact, as we come to the downhill part, you can see many of these objects here that, like this and this, these are all large boulders and when I say large, they're of the scale of the size of this building and the other buildings in this complex. So that would have been quite something to see, although presumably not from inside the crater. I included this picture because this and the other pictures that I've shown you so far have all been in black and white. But of course, Dawn has other sensors, and just like the image I showed you of the surface of Ceres earlier from the Hubble Space Telescope, we can encode some of the other information about Vesta in other colors, and that's what we can see here. And so this shows that, excuse me, there's a lot going on here besides just the topography and the surface shape. What we believe is happening here is there was an impactor that came in this direction, hit here, and then sprayed this orange material out here. And you can see that there are other minerals of different mineral types here and down here and up here as well. And so we can use these different ways of depicting the different mineralogy to show the entire southern hemisphere. So what I've done here is unwrap the southern hemisphere. So this is the equator all the way around here. You can see some of these equatorial chasms here. This is the 300-mile diameter crater and the mountain in the center. And the different colors tell us about the different minerals here. And one of the reasons I like this view is, in fact, because it reminds me of an ashtray that I made when I was in nursery school. But it also tells you an interesting story about the nature of Vesta, because the kinds of minerals that are observed in the center here are the type that form deep under the surface of a planetary body. Whereas the minerals out here, these deep blues and colors like this, are more typical of the minerals that form at the surface of a planetary body. And that makes sense, because this big impact that occurred here excavated material from deep under the surface and left it in the center of the crater. But what had been closer to the surface is now thrown out to more distant places, and that's why it's out here. So that's using the color to show something about the mineralogy. Here now, I'm using the color in a different way, but again, this is the entire southern hemisphere, so this is the equator all the way around here. Once again, some of these canyons near the equator. But now the color is showing you not the mineralogy, but the topography. And of course on Vesta there's no sea level, but just using an arbitrary reference. And you can see the blues are 14 miles below this reference elevation, and the white is up to 12 miles above. And to put this into context, this is the height of Mount Everest relative to sea level on Earth. So the topography here is of an entirely different scale from what you know about from Earth. And so what we're seeing is this and this are the high walls, the surviving walls of this large crater, the 300-mile diameter crater. This is that big mountain with the peak here. And so the summit of this mountain soars to more than 2.5 times the height of Mount Everest relative to sea level on Earth. And part of these crater walls goes up to 3 times the height of Mount Everest. So this is truly extraordinary. In fact, this mountain now is the second tallest mountain known in the solar system. It's almost as high as Olympus Mons on Mars. The difference is actually not that large. But nothing of this scale is on Earth. In fact, even if you go from the bottom of the Pacific Ocean to the summit of Mauna Kea, the change in elevation is not as large as what it is from the plains of this crater here to the summit of this peak. And so if you just think about what it would be like to be in the bottom of this crater with a mountain 110 miles across and robbed it of some of its orbital energy around the sun. And so for those of you who like to keep track of the accounting, we actually slowed Mars down in order to take some of its energy for Dawn. So Mars now travels more slowly at the rate of about 1 inch per 200 million years. But that was enough to help Dawn along its way. And in July of 2011, we got to Vesta and went into orbit around it, spent 14 months there, and then we left, and the spacecraft is now on its way to dwarf planet Ceres, which it will reach in a little bit less than a year. And at each destination, we make a comprehensive set of measurements. Of course, we take photographs of the surface. We're all visual creatures, right? We like to see pictures. We also make a topographic map by taking pictures in stereo, and that's how I was able to show you the heights of all these different features. We map the elemental composition, that is, what are the atomic constituents of these bodies, and the mineralogical composition, that is, how do these atoms combine to form minerals, that is, what kind of rocks do we have there. We also measure the gravity field because that tells us how the interior is structured, how the material is organized. And so, for example, at Vesta, one of the things that we've learned from that is that Vesta, like Earth, has a dense iron-nickel core. Now, Earth's is molten, Vesta's is no longer molten, although it's believed that it used to be. And surrounding that dense iron-nickel core is a lower density mantle and then a crust above that. And we searched for moons because certainly these bodies are large enough that they could have moons, although, as it turns out, we didn't find any at Vesta. So this is really a comprehensive mission of comparative planetology. But now this brings up something interesting. Dawn is not only the only spacecraft ever to have orbited an object in the main asteroid belt, but it's actually the only spacecraft in now 56 years of space exploration, the only one targeted to orbit any two solar system destinations. No other spacecraft has ever planned to do that. When you think about it, that's sort of a surprising thing. It seems like a very logical kind of mission to undertake, and it's not as if nobody ever thought of it, right? It happens in science fiction all the time. Go to some planet, do whatever you're going to do there, beat somebody up or make out with them, and then go to some other planet and do the same thing. And yet this has never been tried in more than 56 years of space exploration. And so that raises the question, why is that? Why have people never tried to do that? Well, once again, for asking that question, I appreciate it. You're a really great audience. The reason is because until recently, engineers were confronted with a problem. They were confronted with the same problem as these two fellows. That is, we just haven't had the technology to carry it out. It turns out a mission that would orbit two solar system destinations is far, far, far beyond the capability of conventional chemical propulsion. It would be truly impossible with conventional propulsion. So not too long ago, in the 1990s, a few of us got together and asked the question, how can we travel around the solar system more easily and less expensively? And our answer to that, as you're not surprised to hear, is ion propulsion. Now, if you're like me, and I know some of you probably are, the first time you ever even heard of ion propulsion was in science fiction. And in fact, this is the Star Wars TIE fighter that Darth Vader and the evil Empire used to fight Luke Skywalker and the members of the Rebel Alliance. And in the Star Wars universe, the TIE fighter, TIE, stood for Twin Ion Engine, because this was one of the most futuristic, coolest, advanced technologies George Lucas could think of. And to me, one of the fun things about working on a project like this is getting to turn that science fiction into science fact. So this is the fact of ion propulsion. And I'll just give you the brief overview of how it works. We start with the gas xenon, which is like helium or neon, but heavier. And we introduce it into a chamber here, which is about 1 foot in diameter. And we bombard the xenon with electrons, much like, if you're old enough to remember televisions from the 20th century, they have an electron beam in them, a beam of electrons much like that, and that imparts a little electric charge to the xenon. For some people here, what that means is this electron essentially bounces off the ion, but knocks another electron off. So we remove an electron. When the xenon atom is charged, it's called an ion. And when it has an electric charge, it can feel the effect of a voltage. And so we have a metal grid right here, and another one right here. There's two grids that are very close together. They're separated by only about 10 times the thickness of your hair, or 20 times the thickness of my hair, and put about 1,300 volts between them. And that voltage accelerates these xenon ions out to the right. And the action of an ion going to the right causes a reaction that pushes the spacecraft to the left. And because we can accelerate these ions to such high velocity, 90,000 miles per hour, each ion traveling to the right imparts a relatively large push back on the spacecraft. And so this system is very, very efficient. It's 10 times more efficient than conventional chemical propulsion, which means for the same amount of propellant, we can undertake missions that are much more ambitious. And so that's really the key to being able to orbit two solar system destinations. And this is a picture of an ion thruster operating in a vacuum chamber at JPL, where I work in Pasadena, which is only about 5 miles from here. And you can see it really does produce this cool blue glow like in science fiction movies. And the reason for that is xenon just happens to glow blue, like neon just happens to glow orange. Now, although the thrust is very efficient, again, it's so efficient, this is like having your car at 300 miles per gallon. We only flow a very small amount of xenon through the thruster at a time, literally just a few milligrams per second. And so, despite the thrust being very efficient, it's also very gentle. And to illustrate that, I'm actually going to do an ion propulsion experiment right up here in front of you. And this is pretty safe. You can do this yourself at home. That is, the ion thruster pushes on the spacecraft as hard as this piece of paper pushes on my hand. And yet, in the zero-gravity, frictionless environment of space, gradually the effect of this thrust can build up. So it would take Dawn 6 days to accelerate from 0 to 60 miles per hour. Doesn't exactly evoke the concept of a hot rod. But instead of thrusting for 6 days, if you thrust for a week, or a month, or a year, or as Dawn already has for nearly 4.5 years, or as Dawn ultimately will for 5.5 years, you can achieve fantastically high velocity. And so this is what I like to call acceleration with patience. In fact, Dawn has changed its own velocity by far, far more than any other spacecraft has. Like this one spacecraft has changed its velocity so far by nearly 22,000 miles per hour. That's well in excess of what it takes to get from the surface of Earth to low Earth orbit. And of course, that requires a large multi-stage rocket. This is what Dawn has done all by itself, a single spacecraft. And we still have a substantial amount of thrusting left to do. And so this really, again, is the key to why we're able to take truly a unique mission. Now, I told you that the idea for ion propulsion has been around in science fiction for a long time. Again, because of the limitations of the time of my talk today, I can't give you the entire history of ion propulsion. But I can tell you that the idea for it has been around for quite a long time. But the first mission really to use it to go someplace was Deep Space One, which we heard about in the introduction. I was lucky enough to work on this mission as well. And DS1's objective was to test ion propulsion and other advanced technologies on an operational interplanetary mission so that then they could be used for more ambitious missions like Dawn. And after we had finished the testing of ion propulsion on DS1, we had a healthy spacecraft out there in the solar system, and so we proposed to NASA headquarters that we undertake the so-called extended mission, which headquarters approved, and we went on to, But you probably didn't hear much about this because we did it in September 2001 when the world's news was focused on other topics. But what matters for the Dawn story was our testing of ion propulsion, and so I just want to show you an artist's concept of that. And there we go. So this is the spacecraft after it's separated from the rocket, extending its solar arrays, leaving the moon and the Earth behind. And once we got it in space and checked out, we started operating the ion propulsion system and ended up operating it for a combined time of nearly 2 years, achieving what at the time was the largest velocity change plane spacecraft, subsequently eclipsed by Dawn. And so that showed we were ready for a mission like Dawn. But before we leave DS1, I just want to show you my favorite photograph of the spacecraft. And that's here. This picture was taken by the 200-inch telescope at Palomar Mountain that maybe some of you have visited. And at the time this picture was taken, DS1 was 9 times farther away than the moon. This is one of the greatest distances at which a human-made artifact has been imaged from Earth. For you astronomers, DS1 was visual magnitude 22.5 at the time this image was taken. For the rest of us, what that means is it was 4 million times fainter than you can see with your naked eye. And in fact, this highly overexposed star here is visual magnitude 12. And of course, as we all know, when large telescopes take pictures of the stars, the telescope needs to rotate in order to compensate for Earth's rotation. That's what keeps the images of the stars here nice and confined. So this shape here doesn't actually tell you anything about DS1's shape. Rather, what it shows is DS1 had its own independent motion through the cosmos at the time this picture was taken. And I worked with the spacecraft every day. I visited in the clean room at JPL, again, just a few miles from here. But this is my favorite picture of it, because what this shows me is we have a spacecraft out among the stars. And I think that's really neat. So that's DS1, but let's get back to Dawn, which is shown here in an artist concept. And the first thing you notice is that it's dominated by these huge solar arrays. And of course, these convert the light of the sun into electrical power to operate the spacecraft. And the reason these solar arrays are so large is because Dawn is traveling far from the sun. Sunlight is weak, and so you need a large area of solar cells to capture enough light to produce electrical power and operate the ion propulsion system. It takes a lot of power now to ionize and accelerate that xenon. This is a real power trip. And enough power to operate the rest of the spacecraft as well. And in fact, at the time that Dawn was launched in 2007, this was the largest interplanetary spacecraft NASA had launched. In fact, if the spacecraft were in this room and one solar array tipped toward this wall, the other one would go 1 inch beyond the wall at the other end of the room. So this is a very large spacecraft. It's the distance from a pitcher's mound home plate in a professional baseball field. And for scale, our main antenna here is 5 feet in diameter. And this is one of our ion engines here. You can see a second ion engine here. And boy, there's a third ion engine there, so we actually do the Star Wars TIE fighters one better. So that's an artist's concept. This is a photograph of the spacecraft when it was being built in a clean room. And you can see this is one of the solar arrays here. And this is another solar array here. And of course, they're folded up because you can't fit a 65-foot wide spacecraft inside the nose cone of a rocket. These are some of the sensors, cameras, and spectrometers up here that we used for studying Vesta and Ceres. This is one of the ion engines, and this 1 foot diameter metal grid here has 15,000 little holes in it through which we shoot the xenon ions. And the xenon is stored in a tank inside the main spacecraft structure here. And because I mentioned now xenon a number of times, I thought I'd show you a photograph of xenon. So this is xenon. Actually, it's my chameleon xenon. And because of his bluish-green color, he has kind of a cosmetic affection for xenon. And he gets a kick out of being included in my public presentations. When I go home tonight and tell him a whole bunch of people at Spacefest saw a picture of him, he's going to think that was really cool. But let's get back to the spacecraft. So this is the spacecraft. Here again is the main spacecraft structure with some of the sensors on top. This is that 5 foot diameter antenna. This is Tom. And this is one of the 2 solar array wings at 27 feet. Each wing is the width of a singles tennis court. This is a very large spacecraft. And I don't know about you, but I think spacecraft are neat to look at. I mean, they're neat things, right? They're neat. I think most people Spacefest think spacecraft are neat to look at. But to me, neater than what spacecraft look like is what spacecraft do. And so I'd like to spend a moment talking about what spacecraft do, because we use them to go far from home. This, of course, is home. And to the accuracy I can do PowerPoint, this is low Earth orbit. It's not very far away. In fact, the distance from the surface of Earth to low Earth orbit is comparable to the distance from here to San Diego. And most of you here today travel much farther than the distance from the surface of Earth to low Earth orbit. It's space, but it's not very far away. And this is where many spacecraft, including the International Space Station, the Space Shuttle when it was flying, where many of the gentlemen out there went, a lot of spacecraft go there, not very far away. So let's change the scale here a little bit and introduce geosynchronous orbit. As I'm sure most of you know, geosynchronous orbit is where a spacecraft takes 24 hours to go around Earth once. And so if a spacecraft is going around in 24 hours and Earth is rotating in 24 hours, then from the perspective of this location here on Earth, the spacecraft is always in the same place in the sky, or the spacecraft always has a fixed view of the surface of Earth. And so this is a very convenient location for weather satellites, communication satellites, and other spacecraft if you want to have a fixed view or that you want to appear to be at a fixed location in the sky. And at 22,300 miles, geosynchronous orbit is far away. That is a very long distance. It's a distance large even compared to the diameter of our planet. That is a very long way. And in more than 56 years of space missions, the overwhelming majority of spacecraft have gone to somewhere between geosynchronous orbit and low Earth orbit. Okay, now with that, let's introduce the next scale. I'll put Earth down here, bring back in geosynchronous orbit, and now the moon, and I'll put the moon up here where it belongs at the same scale. The moon is very far away. The moon is 250,000 miles. The moon is 10 times the distance to geosynchronous orbit, or 30 times the distance, 30 times the diameter of our planet. The moon is very far away. And as most of you know, at least this is what I've heard as a rumor, that sometime in the distant past, 24 men had traveled the distance from the Earth to the moon. At least that's what our ancestors tell us, and there's some people out there who would make the same claim. Whether it's true or not, I don't know. But what this tells us is, this picture is of the scale of the entire range of firsthand, personal human experience throughout all of human history. Because people don't travel the distance to the moon anymore. People don't do that. People only go a distance comparable to the distance from here to San Diego. So for all of human history, human experience is contained in a picture of this scale. And the day after dawn launch, we passed the orbit of the moon. We launched on September 27, 2007, and on September 28th, we had the moon in our rearview mirror. So now let's bring in the next scale. This is Earth's orbit around the sun. And as the Earth goes around the sun, of course, it brings the moon with it. So let's bring the sun into this picture. This is the sun. And at the scale of the sun, this is the size of the orbit of the moon. And this is the size of Earth to the scale of the sun. The sun is 109 times the diameter of the Earth. The sun is large even compared to the orbit of the moon. The sun is large compared to the entire range of first-hand, personal human experience throughout all of human history. The sun is 865,000 miles in diameter. From this, we can conclude the sun is big. So, with this sense now of the size of the sun, let me put it down here in this corner. And up here, I'll bring back in the orbit of the Earth, which I'll magnify for just a moment. And this blue is the orbit of the moon. The Earth itself is much, much too small to be seen on this scale. So, there's the orbit of the Earth, the orbit of the moon, the sun, and dawn was as far away as the sun in February of 2010. And in fact, this last November was 3 times as far away as the sun. And indeed, in a little less than 2 years, it'll be 4 times as far away as the sun. And at that time, it'll be more than 1,500 times farther from Earth than the moon. It's already well in excess of 1,000,000 times farther away than the International Space Station. And I think this is really incredible. And corny as it sounds, and believe me, I know it does sound corny. On missions that I've worked on where the spacecraft has gone on the far side of the sun, I've gone outside and put my thumb up and thought, gosh, we have a spacecraft on the far side of the sun. This is the same sun that shone down on our planet for 4.5 billion years. This is the same sun that's the source of virtually all of the energy our planet has ever had and will ever have. This is the same sun that's 1/3 of a million times the mass of our planet. This is the same sun that's the gravitational master of our solar system. This is the same sun that's our signpost in the Milky Way galaxy. And yet, we have spacecraft farther away than that. And when I say we, I don't mean me. I don't mean my team at JPL. I don't even mean the entire engineering and science community. I mean everyone. To me, everyone participates in a mission like this. I think anyone who has any curiosity about the nature of the universe, anybody who's ever looked up the night sky and wondered what really is out there, anyone who really wants to understand how we fit in to the larger universe, for that matter, anyone who feels just that burning passion for exploration, the desire to go beyond the horizon and see what's there. I think everyone participates in a mission like this. This to me truly, like other interplanetary missions, truly is a mission of humankind. I think of these, in fact there's a book out there with a similar title. These are robotic ambassadors from humankind to the cosmos. And that to me is what's really cool about missions like this. I think that's what's the most remarkable about these interplanetary missions. Canaveral on September 27th. In fact, just near dawn, and you can see the sun rising in the background there, and got off to a very nice start. And then once we got in space, this is the trajectory we followed, again with the conventional view. So here's the sun in the center, and the orbit of Earth here. This is where Earth was when we departed, and if you care, when it's this nice chameleon xenon blue color is where we're mostly thrusting, and where it's dark is where we're mostly coasting. And so we started out coasting, and then we operated the ion-propulsion system for some tests and operated some other subsystems. Once we got things checked out, we got into a pretty regular pattern of thrusting most of the time, and in fact, actually we thrust more of the time than is indicated here because the software that generated this plot exaggerates the duration of these coast periods. But we thrust most of the time. Then we had this 7-month-long coast period during which we decided to slow Mars down a little bit in its orbit, then continued thrusting, so we gradually spiral outward from the sun, slowly matching orbits with Vesta until we got to it in July of 2011, went into orbit around Vesta, and then stayed with it for 14 months, then used the ion propulsion system to get out of orbit, and we're now undertaking this long climb out to Ceres, and in fact we can zoom in and see where dawn is today, and that's where it is, and as long as we're zooming in, we can see where Ceres is, and it looks like they're very close together, but they're still about 9 million miles apart, so there's a little bit of a ways to go. And we can also see where Vesta is. We've now long since left it behind, and as long as we're zooming in, we can also zoom in to see where Earth is, and that's where Earth is, and oh boy, actually that's where we are at the convention center. And so the spacecraft will continue along until it gets to Ceres in late March or early April of next year, go in orbit around it, and then spend the rest of its time there. Now, when you look at a picture like this, it's flat and it's static. And it's easy to forget that the solar system really is in motion. It's a very dynamic place. I like to think of it as having this big, beautiful, complex choreography. And so what I'd like to do is show you an animation of it. That's actually what I'd like to do, but it turns out the animation doesn't run in PowerPoint, and so I've run into a little bit of a rough spot in what I hope has been a smooth presentation, so I have to get us out of PowerPoint for a moment to get us set up here. Okay, so before I get it started, let's orient ourselves again. So here's the sun. This is the orbit of Earth, Mars, Vesta, Vesta, and Ceres. And Vesta's going to make 1 1/4 revolutions before we get there. Ceres will make several circuits as well. And so here's Earth, and when we launched in 2007, the spacecraft is on its way thrusting toward the flyby of Mars. So we had this long coast period during which we flew by Mars, and then after that resumed thrusting, aiming for Vesta, but we won't get to it until here, and Ceres still has another full revolution before we're going to get to it. Excuse me. So then in mid-2011 we got to Vesta, went into orbit around it, spent our 14 months there taking all of our data, resumed thrusting, and now we're on our climb out to Ceres. And as we're walking, you can also see we're moving down toward what's called the ecliptic, or nearer the plane in which Earth orbits. And you can see Vesta and Ceres have quite significant angles relative to the ecliptic, which makes this mission only that much more difficult, but the ion propulsion was up to it. And so then the spacecraft will have gotten into orbit around Ceres, and that's where the mission will conclude. Whoops. Let's see if we can. Here didn't seem to appreciate that transition. Okay, so that's the overview of the mission. Again, it's the ion propulsion that really allows us to explore Vesta and Ceres. But now, you're probably wondering, how many times am I going to tell you how important the ion propulsion is? And you know what? Most of you have never heard of me. You don't have any reason to trust me. I don't bring any credibility here. And so, as much as many of you have already inferred, I brought along a recorded testimonial from some people whose job it is to tell us what's important about the future. These are people in whom I think we can have a lot of confidence. These are people who think about technology and the future and what really matters. And so they're people who I think can guide us and tell us what we should really be paying attention to. So let's hear what it is they have to say about this. Don't worry, we're not going to watch the whole episode.
Base and standing by. And 43,000 in the world. What do you read which spot? Configuration unidentified, ion propulsion, high velocity. So, unique technology. Any contact with them?
On all frequencies, several languages have been attempted, no response. Now using standard interstellar symbols.
Keep trying. Identification 10. Well done. See, isn't she a beauty? Interesting design. I've never seen anything like her. And an ion propulsion like that.
If you have the stomach to sit through the rest of that episode, later on you can hear Captain Kirk say to the bridge crew, "Advanced ion propulsion is beyond even our capability." But you know what? Not beyond our capabilities now. So the first time, actually that's the first time I ever heard of ion propulsion. My older brother watched Star Trek. I think it was probably already in reruns, but I remember seeing that episode, that part of it, and thinking, never occurred to me I'd grow up, and to the extent I actually did grow up, get to work on a mission using ion propulsion. So that's sort of the long view of the mission. As you can imagine, we're very busy. We have things going on all the time. I'm not going to bother you with every imaginable detail of what we're up to. Instead, I will just thank you very much for your attention, and I appreciate your letting me tell you about what's going on.